For the second part of the electricity crash course video, we need to look at internal resistance as well now. And please, I need you to know that it's just another resistor. And you must see it as another resistor just taking energy as well from the circuit. We've already spoken about the battery and the EMF. So what we said is if we connected a voltmeter here across the battery, that voltmeter will tell me the because the switch is open, that means there's no flow of electrons at the moment, no coulombs leaving the battery. But this still tells me the maximum amount of energy available because of the chemistry that goes on inside the battery, the maximum energy per coulomb that the battery could give. So now what happens is, in an ideal world, what would happen is if the EMF of the battery, and this would then be the EMF. So if the EMF of the battery is 5 volts, as we spoke about earlier, in an ideal world, all 5 joules of energy per coulomb, remember voltage is joules per coulomb, every coulomb that leaves will leave with 5 joules of energy. Now, if I close this switch, they can start to move, and then this voltmeter will tell me, remember, what's gained in from the battery, but also what is given off on the outside. So it will tell me then that this light bulb also uses 5 joules of energy per coulomb. So the reading there will also be 5 volts. But now we don't live in an ideal world, and they cannot make a perfect battery. And because of that, batteries inside, because of the way the battery was built, there could be some resistance. And we give us the symbol small r to that resistance inside the battery. Now, as the light bulb uses energy because of its resistance, the battery will also use some energy because of its resistance. But what it means now, the 5 volts or the 5 joules that I had available, so the EMF is still 5. So if the switch is open like it is now, even if there is internal resistance, this will still be the EMF. So the 5 will still be the EMF. Please remember that that is constant. But now, as soon as I close the switch with an internal resistance, it means that some of the 5 joules will now be used inside the battery according to the internal resistance, which is also a constant. So some of the energy, some of the 5 joules will not reach the outside. So let's say this battery of ours uses 1 joule of energy per coulomb. So remember that will be 1 volt is being used inside the battery. Now, some people calls it lost volts. Some people calls it V internal. It doesn't matter what you call it. It's the energy that is used inside the battery. We'll go to the equation now, and you'll see that we are going to call it the voltage due to the internal resistance. You're welcome to just call it V internal. So now if 1 joule is used inside the battery, then this reading here, the coulombs that are leaving are not leaving with 5 joules anymore. And when they come back, they are not going to gain 5 joules anymore. So this reading actually tells us now the external voltage and also the amount that the the coulombs are going to gain from the battery. So it's not going to be 5 anymore. So if I now go and connect a voltmeter here, this voltmeter as well as this voltmeter will not read 5 anymore. It will now, I hope you have been thinking this, read 4 volts. And this will now also be 4 volts. So that's where this equation comes from. The EMF is the total amount of energy that the battery can possibly give. But then sometimes that is equal to V external. Okay, that could be equal to V external if there is no internal resistance. But sometimes some of that energy is going to be lost inside the battery, lost in inverted commas because it's not totally lost, but it's not just not available for our light bulb. It's not useful energy. So this will then be V internal. The V external is anything that is in the external circuit, and you'll see on your information sheet it's called V load, but it's the same as the V external. Now, what they often ask in an exam is if something is changed about a circuit, how will that reading change? So you will have a voltmeter connected across your battery here, like we had. And now remember, if there's no internal resistance, this voltmeter will give us the EMF. Also, when the switch is open, that voltmeter will give me the EMF. But if the switch is closed and there is an internal resistance, they normally mark it with a little r. If there is an internal resistance, this internal resistance will then cause some of the energy to be used inside the battery. So now that what the questions are going to say, you're going to have a setup like this typically, and they're going to say, what's going to happen if I now go and put something extra in parallel? Or they can say, I'm taking something extra away from parallel. Now, please remember, if the switch is open, this reading will still just be the EMF. Okay. Now, but when it's a closed circuit, we now need to see it's not going to be the EMF. What is going to happen to this reading here? So if it was 4, is it still going to be 4? That's what we need to think about now. So you have to see what is the change. It had one light bulb, like it was at the top. It had one light bulb, but now I'm placing an extra one in parallel. Now, you need to realize by now that if I place something in parallel, I'm opening another door and making it easier for the electrons to flow. So if 10 electrons per second could flow there, so 10 ampere, and I open the same extra door, then another 10 could flow there. So my current will actually go up to 20. So now what's going to happen is in my current, because my resistance is going down, I'm making it easier for the electrons to flow. As the more things I connect in parallel, the easier it is for the electrons to flow. So my resistance is going down. And because my resistance is going down, and you can calculate that with maths, but you can also reason it out, the current is going to go up. Now, here is where I'm just going to quickly remove this, that I can have some space to scribble. So what's going to happen here, and this is where you get your second equation. The V external is what we are asked about, because this reading is giving me V external. So they're asking me what's going to happen to V external. But what you need to remember that V internal, the same current flows externally and internally. The electrons that passes through the battery must pass through the external circuit eventually. So the current here is going to be the current there as well. But the V internal is equal to I times R, like all things, all V's are I times R, remember, according to Ohm's law. So now, if you look at what's happening here, the current going up here, internal resistance stays constant. That's very important. The current going up here will mean that this whole V internal will go up. So that means more energy is now being used inside the battery. And that should make sense to you now, because if more internal energy is used inside the battery, there is less available for the outside. But you can also reason it out using the maths, because EMF is a constant. And because EMF is also a constant, if the internal voltage goes up, then the external voltage must go down. Please remember that you do not use Ohm's law to answer these questions, because it's not for the same resistor. And that's the only time you can use Ohm's law. The same would happen, I'm just going to go through it very fast now. The same would happen, or not the same, but they could ask you as well, what is going to happen when you take one of these parallel branches away? What will happen to this outside voltage if you take a parallel branch away? Now, remember, there were 2 doors open, easy for the electrons to flow. Now I'm taking this branch away. So the 10 coulombs per second that could go there can't flow anymore. So I'm making it harder for the electrons to flow. So my total resistance is going to be higher. And because it's now harder for the electrons to flow, there will be less electrons flowing per second. So the current is going to go down. And then, similar to what we had before, the EMF is still constant, is equal to the V energy that's used outside plus the energy that is used inside. But this energy inside, so I want to know what the V external is going to be. This V internal again is equal to I times R. Little r is constant. If the current here goes down, that means that this whole V internal is going down. But because the EMF is constant, if the internal voltage is going down because less energy is used inside the battery, then that means there is now more available for the external circuit. And therefore, this external circuit reading will go up, and that means this reading on my voltmeter will go up. Please remember that this is only for when there is internal resistance. Otherwise, the EMF and the external voltage will be the same. The second equation here is basically just the mathematical simplification of this one. So please understand it rather than just rote learning that equation, because it's often used wrong by people that don't understand what's going on in the electric circuit. So the second one is just saying, all right, this is equal to I times by the external resistance plus I times by the internal resistance. And because the currents are the same, we can say that that is R plus R. And if your maths is very good, sometimes you might feel more comfortable using it, but still make sure you understand where this comes from. It's the EMF, which is the total amount of energy available that is split up between the external voltage, what the light bulb is using, the energy that the light bulb is using, and the energy that the battery is using.